Okay, I'm going to tell you something about a sort of alternative picture of the quantum Hall effect, which I'm pushing. And basically, let's move to the first slide. Garbled. Most condensed matter systems with no low energy electronic excitations are insulators, where the electron density is completely controlled by the elastic degrees of freedom. So the electron density is basically proportional to the volume of the unit cell, of the volume of the boron zone of the crystal, and the number of electrons in the unit cell is fixed. But quantum Hall systems are an alternative kind of electronic system with no low energy electron excitations, where the other degrees of freedom inside the material, the electromagnetic degrees of freedom have captured some of the electrons. So again, you have no low energy degrees of freedom. So everything inside the bulk of the gapped region is controlled by the electromagnetic field, but those electrons were stolen away from the lattice and have been siphoned off by the electromagnetic field. So let's just quickly review the zeroth order description of quantum Hall fluids. And so the baseline description will be the topological field theory of U1 level K Chern-Simons theory. And we can think of this system, we can think of it as having a boundary. Does this work, by the way? No, it doesn't, right?
No, that's cool.
Yeah. Oh, I have to use the pointer or something like that, right? The mouse.
I'm going to show. Yeah, it's not going to work.
It's not going to work. Okay. So okay, so the basic picture then of a quantum Hall droplet is some region in which this condensate controlled by the electromagnetic field has occurred, and the Chern-Simons theory is the basic description of, without any details of geometry and deviations from just being a uniform density structure. What can we just say about this? If you actually look at the Chern-Simons theory, it's there's a level structure, level K in the U1, which I'll explain why you have a quantization of abelian Chern-Simons theory. And the basic property is that I'm going to say the Chern-Simons field describes the composite boson, which is going to be the elementary unit of the quantum fluid, precisely analogous to the unit cell of a crystal. So just as a crystal is built up of an array of elementary units, the incompressible quantum fluid has also a structure of little units, which in this case will be composite bosons. So there's a place for the composite fermion picture too, but it's not in this fundamental description. The composite fermion picture will be very useful in discussing transport in doped quantum Hall systems, but the composite boson is the essential analog of the unit cell. So it's got a certain number, it's got an electric charge Q0, and the Chern-Simons theory doesn't know anything about the detailed structure of the condensate, okay? It doesn't know, the only things it knows about the composite boson is the total charge of the individual unit, which I've called Q0. And it knows about the level of the Chern-Simons theory. And so far, I haven't related those at all to the microscopic details. Yeah.
Are you using the gauge where A0 is 0, or because I only see the space?
Yes, I don't believe there's any use for A0, so it's a non-variable, right? It's a Lagrange multiplier, which isn't necessary. Okay, so the only dynamical variable in the problem is the vector, the Chern-Simons vector potential. And okay, so in this case, the Hall conductance of the system is K times whatever the now I can't use this thing, right? K. I can't use this either, right?
It's potentially
yeah. Okay. So here's an antisymmetric symbol. So K really only occurs multiplying by an antisymmetric symbol. And we have here the charge squared on the composite boson, and here H bar K times the level of the Chern-Simons theory. And the basic quantization condition, well, K is going to be an integer because for the next slide, I'll explain it. But -1 to the K has just to be equal to the fermion parity of the particles which are contained inside the droplet, the elementary units, the elementary unit. And in the interior of the fluid, the flow velocity is completely controlled by the electromagnetic field. It's basically the drift velocity. And I'm going to use the Faraday tensor rather than magnetic field because there's no, the magnetic field is ambiguous and you have to choose handedness conventions, and Faraday is a completely unambiguous form. So of course the Chern-Simons theory then gives you, expresses the composite boson electric charge density and the composite boson electric current density. And in the interior of the fluid, there's no internal degrees of freedom at low energies of the fluid itself. So everything, the flow velocity is completely determined by the electromagnetic field. Okay, so what's the microscopic picture? So the composite boson is this elementary unit, and it occupies an area which is fixed by the magnetic flux, which I'll use as the square root of the determinant of the Faraday tensor, which is always has a positive determinant. And it contains p electrons and covers an area with q electronic or London flux quanta. So we now have a load of internal structure here. It's got a fixed area, it's got a shape, and it's got some stuff inside it, which are whatever the elementary charge is. And in this case, we see it's made out of electrons. And yeah, the other thing we're going to say about it is one of the most fundamental properties of the composite boson is it has an inversion symmetry. Okay, so it has an inversion center. So when the fluid is not flowing, the composite boson has exactly zero electric dipole moment of the distribution of charge inside it relative to the center. And the fundamental symmetry of the quantum Hall effect is unbroken inversion symmetry. It's very fundamental, and in fact, I'll probably explain later that the one profound consequence of this symmetry of inversion symmetry is that the two independent numbers you see, p, the number of electrons, and q, the number of London flux quanta in the going through the area of the boson, can only have a common divisor of 1 or 2. Okay, that's not an obvious thing, but it follows absolutely from the condition that the vacuum state of the quantum Hall state is an inversion symmetric state with a gap for all states which carry broken inversion symmetry or electric dipole moment. The gap in the quantum Hall state is not a charge gap, it's fundamentally a dipole gap. Okay, and the other thing about it means that composite bosons have a definite parity. One of the things which indicates the species is whether it's even or odd parity, and parity here means two-dimensional parity, which is 180-degree rotation in the 2D plane, not 3D parity where no mirrors are involved in it. So given these two numbers p and q, the level of the Chern-Simons theory k is equal to pq, and the elementary topological excitation carries a charge given by 1 over k times the charge of the element of the composite boson. So we can actually determine, of course, from that what the individual, we know the ratio of p and q if we know the electronic filling factor, p over q. But if we know the charge of the elementary topological excitation of the theory, we know p and q independently. Okay, and as I say, the Chern-Simons theory level is actually the product of these two numbers. Okay, so why is the abelian Chern-Simons theory, why does it have quantized levels, right? If you go and read up Westerminer-Witten theory, you'll see that quantization is something only seen with non-abelian Lie groups, right? Well, of course, the quantization of the U1 Chern-Simons theory is fundamentally the condition that the elementary object by the gauge field to be either a fermion or a boson. Then there's a selection rule that it's got to compensate the intrinsic fermion parity of whatever the particles that sit inside the thing are. So if I take a look at the actual Chern-Simons part of it, it's actually a little empty region of area 2 pi QL squared, which has an inversion center. And where does the Chern-Simons gauge field come from? It's nothing to do with kind of gluing magnetic flux onto particles in the old way that was thought about in the early 80s and 90s. It's of course it's this void, this bubble or vacancy, a hole in the background fluid, which when you drag it around, it sweeps the other particles out of the way and picks up a Berry phase as it moves around. And the Chern-Simons gauge field is describing the Berry phases generated when this empty bubble or hole is dragged through the incompressible quantum liquid background. And flux attachment just means that the p particles that are going to live inside this little bubble occupy it to the exclusion of all other particles. So the kind of generalization of the Pauli principle, in fact, you can understand the integer Hall effect rather nicely from this viewpoint. It would seem to most people that it's obvious that the integer Hall effect should be understood in a fermionic language, right? You fill some Landau level up. But actually, if you look at Landau levels, let's think what happens if I make a hole in a Landau level. I pull a particle out, okay? What's left behind? Of course, the magic of quantum mechanics has showed that a hole in a semiconductor behaves like a fermion, right? Well, in a lattice system, in some sense, the orbitals in which the electrons live, they're kind of tied to the atoms, right? You kind of hop from one Hubbard model orbital to the next, hop, 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 hop. But actually, there's no underlying structure to which an orbital, the orbital which will be filled by the electron, is attached. So you can adiabatically move this orbital around. The empty orbital can be adiabatically moved around in the background of the filled orbitals and continuously moved. And of course, by this thing, it'll actually generate a U1 level 1 Chern-Simons field by being dragged around, okay? So, and we know that the hole is a fermion, so if I actually fill it, I put with an electron, I've coupled two fermions together and I've got a boson. So actually you can come up with a perfectly rational and consistent description of the integer Hall effect in terms of the composite boson theory too. Now there's one difference between the integer and the fractional thing is that there's actually no natural geometry of the hole in the integer effect, while because basically there's a principle that if you completely fill an orbital, a band rather, it's invariant under an arbitrary change of basis of how you fill it. You don't need to fill it with orthogonal. You just stick a linearly independent set of orbitals. You fill them and you orthogonalize, and you've got the states independent of that. When you actually get to the fractional case, because there's actually the electrons will be occupying, will own a larger number of orbitals than given to them by the Pauli principle, then there's an important issue of what shape the bubble takes, okay? So it's only in the fractional case there'll be some kind of dynamical shape associated with the shape of the Chern-Simons gauge field. So as I said, the fundamental symmetry of the problem is the 180 degree or 2D inversion symmetry. And basically it's because the system has a gap has a gap for any excitations that carry electric dipole moment, and electric dipole moment is fundamentally related by the Faraday tensor to momentum. So the polarization density when contracted with the Faraday tensor gives me the momentum density. So what about continuous SO2 rotation symmetry, which is a totally popular thing in most people's treatment of the quantum Hall effect? And it's a feature of the toy models, the Laughlin state, that people use that's been extremely useful in understanding flux attachment. And most people would automatically write down rotational invariant states and start to attach meaning to things like angular momentum and base all kinds of constructions on rotational symmetry. My message to that is it's a profound and deep error to include this symmetry in anything that's supposed to give you a fundamental description of the quantum Hall fluids. So why is that? Why would I assert that? First of all, in any condensed matter system where you have a fixed crystalline background, which we do in this case, there is no continuous rotation symmetry. There is no such thing as angular momentum as a conserved quantity in them. There may be some approximate vague conservation laws, but there's absolutely no continuous rotation symmetry of condensed matter. This doesn't apply to liquid states. Liquid states, liquid helium and things, perfectly good rotational symmetry, but once you've got the crystalline background, there is nothing left behind for an angular momentum. So if you start to play with toy models which have a rotational symmetry and you build your world on it and think you've explained anything, you've fooled yourself, okay? And even spin angular momentum, of course, is pretty well conserved because it's only violated by spin orbit coupling, but it's really not a rotation symmetry anymore, because if you don't have the spin orbit coupling, it's actually just an internal SU2 degree of freedom rather than anything connected to angular momentum. It happens to have, say, Lie group, but that's about it. Okay. So there's an approximate isotropy on 2D square and hexagonal lattices, but there is the quantum Hall effect. The lattice symmetry is important in various crystalline type topological insulators. There's lots of interesting things that happen for special cases of corners of cubics and things like that. But in the quantum Hall effect, there is none of these lattice symmetries are protective symmetries, right? So you're absolutely barking up the wrong tree if you include unrelated symmetries which have no relation to the fundamental system, right? That's why it's not a protective symmetry. You should not include it in your theory. Okay. Yeah.
Inversion symmetry is also.
Inversion symmetry will be a fundamental symmetry. The fundamental symmetry is a symmetry of the clean vacuum. Of course, impurities will break it, but impurities have to break it only sufficiently weakly that they don't destroy the state. There's a clean vacuum state that we want to classify first, right? And the fundamental property of the clean vacuum state will be translation and 180-degree inversion.
So let me ask a little bit. So in particular, it sounds like you're saying if I have, I have a material and it starts off, and it's not some discrete crystalline material. Earlier on you were talking about dielectric constants, right?
Yeah.
Dielectric constant starts off being kind of rotation invariant, and then I do so, I deform my materials of the dielectric constant is now different in the x and y directions. And the claim is that wouldn't change the nature of the.
Yeah, so it's not important. It's in fact, if you actually look at the equations of condensed matter, of course, the internal structure of the atom is determined by the high energy structure. It's round. That's why atoms are round. They're reflecting the metric of flat space time, right? But once you go to scales large compared to the atomic scale, there's only actually one place where the Euclidean metric of the vacuum enters, and that's in the effective mass tensor of the nuclear cores, the ionic cores, right? Because they're well described by Newtonian mechanics. So the dynamics of the nuclear positions and any tightly bound electrons in little spherical deep orbitals which are connected to them. They have a mass tensor which is universally given by their gravitational mass times the metric of flat space. So that's the only place you should expect to see the metric of empty space occurring in an honest theory of condensed matter. We of course will use the laboratory frame, which we live in, and we're kind of using it to try to measure the thing. The laboratory frame will be a Cartesian coordinate system, which will be based on the metric of empty space. But it's just an arbitrary choice, our convenient but arbitrary choice of coordinate system. So it shouldn't enter into any of the underlying physical equations. You should never see the metric, except for this one case of that the effective mass tensor of all the nuclear coordinates are congruent with each other. Okay, so the group SO2 has a kind of even higher symmetry extension, which is very popular in this field, which is conformal field theory, right? But we're not talking about Lorentzian conformal field theory. We're talking about the orthogonal conformal group, okay, which is 2 + 0 dimensional field theory, conformal field theory, which is of course a Laughlin wave function and all the nice model conformal block wave functions describing the bulk properties, modeling the bulk properties of certain quantum Hall states are actually toy models which have an even larger symmetry, a kind of super gauged version of SO2 on steroids, okay, which is the conformal orthogonal group. Okay. So lots of really interesting results have been obtained using the conformal block wave functions, and they actually give you the Laughlin state as one of the first, insight into flux attachment, right? But what we actually need to see that some of the results obtained with these beautiful ultra high symmetry toy models, some of them luckily will turn out to be generic, but some of them will turn out to be very specific features of the ultra high symmetry artificial toy model that we're working with. So it's going to be important to attempt to separate what we've learned from conformal field theory toy models, what part of that is generic and what part of that is just kind of specific little things. It's about as if you studied your magnetic spin chain system through the beta ansatz, right? You know that the actual generic situation doesn't have the same kind of integrability and quantum groups and things associated with the beta ansatz. So you should not build your generic theory of of quantum spin chains or whatever based on what you learned from the beta ansatz. You're going to realize that some of the stuff you found in these very special models with extra properties will conform to a generic scheme, but some stuff will be particularly special to the extra symmetries. And another class of very interesting results derives from conformal maps of these conformal block wave functions to map them onto the Riemann surfaces with Gaussian curvature. And one's seen some very nice kind of Salvador Dali type pictures of melted clocks with quantum Hall edge states and stuff. But actually, real quantum Hall fluids occur on crystal lattice planes. Okay, there's never been a quantum Hall fluid on a sphere. And crystal lattice planes do not have Gaussian curvature. In fact, one of the most remarkable things about crystals is you examine a macroscopic crystal and you look at the facet of it, and you see the thing is macroscopically flat over huge distances, right? And even the graphene sheets. So I wanted to have then we've got a sheet of paper handy. I want to just do a question. Just on your pad, right? Thank you. You don't mind losing this, right?
I don't think so. I can't remember what I
Give me a
wrote.
blank sheet. Okay. So let's say graphene is also as a crystal structure, right? Graphene, of course, can easily have this kind of curvature, not the Gaussian curvature, the extrinsic curvature, but You know, that if I sample up this is actually quite a good representation of graphene, right? There's still no Gaussian curvature, or rather, all I've got is cone singularities, right? This stuff has the cone singularities have actually done some intrinsic damage to the sheet of paper. So even if I pull this out and iron it properly, I'll never completely get rid of the damage where the cone singularities happen to allow the thing to crumple. But there was no Gaussian curvature in this at all, right? So with a piece of paper, which is also as resistant to Gaussian curvature because of its fiber structure as graphene. Now I should have a clean one. The best thing you can do is to fold it and you see that all you get is cone structures. So graphene doesn't. So there's just none of the actual physical systems on which the quantum Hall effect has been seen actually they even so resistant they hate Gaussian curvature.
So Duncan, how about like a buckyball?
That's just cone singularities again, right? Anyway, that's not, you can't.
Put a monopole inside.
Yeah, but the singularities are like, I mean, if I take a crystal, right, a cubic crystal, it's got these point singularities. It wraps around the sphere, and it's got eight point singularities. The buckyball is kind of just like that. It's got 12 or whatever. Right?
If you zoom out, then effectively at longer scale, you have Gaussian curvature. It's spherical. I mean, you can imagine a big molecule.
But the curvature is only at the points. It's got conical it's got cone singularities, right?
Depends on which scale you look at. You coarse grain this thing.
Still flat. I mean, you can, of course, you can tile it by having, you can tile it to have, I guess, what you call it, terraces and things, but that's not giving Gaussian curvature. That's just kind of, that's just putting on extra layers.
They do magnetic ones to many units, so.
Anyway, so the question arises.
Looking at them cylinder is okay with you.
Cylinder is fine, but there's no Gaussian curvature. Yeah. So okay. So what remains? So what did all these beautiful results about, you know, the extra part of the density proportional to the local Gaussian curvature on these nice curved surfaces, the Riemann sheets, what do they actually mean? Okay. And actually, we can deconstruct this stuff and turn it into the general thing. And the formulas which involve Gaussian curvature will be still there on the completely flat surface. Okay. And the physical interpretation will not be Gaussian curvature. Okay. So the basic point is that the quantum Hall fluid, the elementary little droplets of the fluid, the elementary units, they have unbroken inversion symmetry, but the distribution of charge inside the composite boson is not a point at the center, right? In the approximation used by the Chern-Simons theory, it's effectively treating the charge as sitting in a point charge at the center of the gauge of the flux, the gauge condensate, the composite boson. But the actual charge is not a point. It's distributed in a non-uniform way inside this composite boson. And since there's no electric dipole moment in the composite boson, at least when it's at rest, then the first non-trivial term in the expansion is the electric quadrupole moment of the composite boson. So the electric field doesn't kind of, the electric field acts at a point. It doesn't act on average over the whole composite of the whole 2 pi L squared area. It acts at every single point inside that thing. So it has to couple to the actual charge density, not the smeared out one that's approximated by the 0th order term in the derivation, which is the Chern-Simons thing. So if you look up quadrupole moments in Wikipedia or something like that, you'll find an awful lot of nonsense. In fact, there's a huge amount of nonsense which is talked about in electromagnetic textbooks, because the standard definition of the quadrupole moment that you'll find is not the correct one. You'll maybe find a small footnote that there is another one, but most of the time people work with what they call the traceless version, right? Well, the trait, of course, if I actually take it, I'm doing my treatment of tensors where all the spatial indices are in their correct positions, right? Because I'm not relying on any metric. So, you know, for example, the Faraday tensor has lower indices. That's because the Faraday tensor is actually part of a two-form, right? And then when I see people in relativity writing FU nu with upstairs indices, I start to shriek because all matter fields have lower indices because they're differential forms. We don't believe that the matter is actually affected by the geometry of space. So, of course, if you can play fast and free with your metric, you can just move your indices up and down at will with a metric, and then you lose track of them, right? But in fact, every index has a proper place, right? A displacement has an upper index because the basis vector, tangent basis vectors have lower indices and differentials have lower indices. So there's a fundamental difference between velocities and forces, or momentum and velocity, right? And of course, when you write your equations in the proper form, the indices on, I mean, I do prefer indices rather than differential forms. So the indices have to line up. They have to match both in the top row and the bottom row. And the only thing you can do a trace on is to contract an upper index with a lower index. Since the quadrupole moment has upper indices because it's got two displacements in it, it's actually meaningless idea to talk about the trace of the quadrupole, to take a traceless quadrupole thing. What people mean by traceless is they're actually trying to solve a Laplace's equation with a particular metric which defines the Laplace's equation. And of course, at a far distance, you have the thing that you can't tell the difference between a fat spherical distribution of charge and a point charge. But we're actually not interested in the long distance field. The thing we're interested in the short distance fields, right? The actual true fields. And so the correct definition of the quadrupole moment is just the variance of the charge distribution, as you can see here. So if I, now have a fluid which is made up of objects which carry both a monopole and a dipole and a quadrupole, etc., I can, of course, take this thing and turn these things into densities and then integrate by parts or whatever. And then I see that what I would call the thing that couples to the electrostatic potential is got the usual free term that we find in things. Now, in a dielectric material, there's a correction term called the bound charge, which is, of course, the minus the divergence of the polarization field. But when you continue, the next term in that is like a half the double divergence of the quadrupole density field. And since we're actually asserting that at least there's no intrinsic dipole in the thing, there's a slight polarization when the fluid moves. So what people worried about in the early days, things like Zhang, Hansen, and Kibelson, and what is the effective mass of every, some kind of Galilean version, which is completely wrong of the the Ginzburg-Landau theory or whatever. The actual mass term is actually the kinetic energy. If you now relate the momentum to the polarization, is actually just the electrostatic polarization. So the effective mass term is actually the fact that when the composite fermion moves, you can actually move the center of charge away from the inversion center. So you generate a small dipole moment. So the kinetic energy is actually just the electrostatic polarization, but the intrinsic one is the quadrupole moment. So we see that the formula that for what actually couples to the electromagnetic field is not just the Chern-Simons charge density and associated current density, but the bound charge part, which is the double divergence of half the double divergence of the quadrupole moment. And of course, dA and one of those divergences get replaced by minus by dt, and I've got the current term which satisfies the continuity equation. So we actually see now that the basic geometric parameter which describes the kind of shape, the basic shape of the composite boson is its electric quadrupole density moment. And the quadrupole density is just given by dividing the quadrupole moment of the individual composite boson by the Chern-Simons density of the composite bosons, okay, or the area of the composite boson. So the quadrupole density has got a nice unit. Its actually unit is just Coulomb, right? The quadrupole density is measured in coulombs. It's a charge because quadrupole is charge times distance squared, and you divide, and density is 1 over length squared, so it's a pure Coulomb. Okay, so actually, if we try to make contact with the nice stuff which was done on Riemann mapping to surfaces with curvature, actually note that if I look at a 2D metric at what's called an inertial point in the coordinate system, a point at which the Christoffel symbols vanish and the metric is just the delta AB, the formal Euclidean metric, we actually get to the Gaussian curvature is basically the double divergence of the inverse metric. And so by the connection, we actually see that those formulas are actually just special cases of the general quadrupole moment formulas, which don't require any notion of, we're not using them to provide a coordinate system for our system. We're actually using the Cartesian coordinate system, which basically the electromagnetic fields live in, right? Of flat space. So the quadrupole moment, just like there's a kind of preferred quadrupole moment. So it's a bit like, you know, a polarized crystal where there's some preferred value of the polarization, but if you apply an electric field to it, you can kind of perturb it away, right? So there'll be some response that if I have a intermittent, so the quadrupole moment couples to the derivative of the electric field. Yeah.
So question, so Q is dynamical for you, right?
Oh, there's going to be a preferred static Q, which is
Q0.
that's the static one that that's the one the ground state, the flat unperturbed ground state likes. Now let me put a little bit of a underlying ripple in the potential on, so there's some, so the electric field has got some derivatives in it, right? So the electric field itself will couple to the polarized. If there was a polarization, the electric field couples directly to that. It's the gradient of the electric field that couples to the quadrupole. Okay.
So what is Q0 for the Laplace, the topic Laplace states?
Oh, well, the Lofton state the Q0 will be proportional to the rotational metric of the Lofton state, right? I mean, the Lofton state is in fact an exact ground state of a toy model which has a rotational symmetry. So if the model has a rotational symmetry, if you make a toy model with a continuous rotational symmetry, it'll pretty well automatically have the ground state value of Q0 will be congruent with whatever the metric of the rotational symmetry is. Now the metric of the Lofton state, so the conformal orthogonal group is not just it's not immediately given to you, right? The conformal orthogonal group is the group of a quadratic form. So it's parameterized by a metric. You change the metric, you've got a different conformal orthogonal group. They may be kind of equivalent or something, right? But they're different, right? The metric enters into the relations of the conformal orthogonal group. So the Lofton state is actually a function of a parameter, which is the metric of its conformal orthogonal group. So there's lots of different Lofton states. They're all parameterized by a metric, okay? And
the simplest one is just 1, diagonal.
No, there's no such thing as the simplest one. They're all equivalent. They're all equivalent but different. Actually, the space of metrics, I'll come to it, is actually SL2R. So the space of this geometry is hyperbolic space. And interestingly, there are two kind of cones, an upper cone and a lower cone in hyperbolic space. one of which applies to it's actually whether the trace is positive or negative, right? I'm going to impose a condition which I think is correct, that in general we're going to deal with positive definite or negative definite quadrupole tensors. Certainly if the charge, there's only one kind of charge in the distribution, it's always going to be positive definite or negative definite. And well, they actually has a kind of handedness associated with them, because one of them, the two instead of a spin in the SO2 algebra, you've got a ladder going from bottom to top. Here we've got either one ladder going from here to infinity, or another one going from here down to minus infinity. One associated with the positive traces, and the other associated with negative traces. Anyway, so the quadrupole density can vary. If there is a gradient of the electric field, well, we certainly have a gradient of the electric field near the edge of the sample, right? We actually don't have a nice. So if the electric field has a gradient in it, there's actually a gradient of the flow velocity around the system, which is of course where you get viscosity coming into the thing, right? So where there's a gradient of the flow velocity. So actually, near the edge of a system, the response, the quadrupole field will be distorted away from the one it likes in the clean bulk, and it'll actually align itself along the directions of differential flow at the edge of the system to kind of conform to the curvature of the potential at the edge, which is the gradient of electric field. If I make a point charge or semi-point charge, like the kind of topological charges you get in the Chern-Simons theory, which actually will result to actually replacing one of the actual topological excitations will not be point charges, but they'll be replacing a composite boson by a different kind, right? But you will actually find that so if you make the simple Chern-Simons theory approach, all that charge is kind of concentrated at a point. But of course, as we know in a dielectric, you actually want to polarize a thing, so you can lower the Coulomb energy by spreading the charge away from the point charge. And indeed, if you make a kind of pattern where the quadrupole density does that around the point charge, is actually, of course, you're not actually changing the total charge of the excitation but what you are doing is you're spreading the charge out in a little fat area where where there's a variation of the quadrupole moment. So you lower so you expect to find this near any point topological defects will be partially dielectrically screened, or whatever, or the analog of that with the quadrupole moment. Yeah.
So once I put this point charge in, if I look at the little circle on the, one of these little circles on the left, which initially only had a quadrupole moment, now, it sees a point charge to its left, but nothing to its right. So it sort of no longer has inversion symmetry. So how do I know that there's no kind of induced dipole moment?
Well, the dipole, I mean, if there's a gradient, there will be there's a local dipole thing, which is just as the double derivative of the thing is the first. There's also a local dipole polarization field, which is the first derivative of the quadrupole moment when it's varying, right? Which actually would be the Christoffel symbols if you try to do a metric thing, right? Yeah.
Yeah, it's getting a bit. So, will you give the stability, this chi ABCD, for some wave functions, or is it known, or how do we?
Actually, it's the fundamental property of the Gervin-McDonald-Platzmann their magnetoroton thing. If you actually look at the if you go to long wavelength of the roton mode, it does something like it comes back up again. If you take the Gervin-McDonald, they got a formula for within the single mode approximation for this collective mode, right? So they didn't actually analyze exactly what the formula meant. They found some junk on the top line, which was proportional to Q squared. and they found some junk on the bottom line, which was actually the guiding central structure factor. And from that, they concluded that there's a gap in the structure factor, better go like q to the fourth rather. So the top line went like q to the fourth. The bottom, the numerator, the denominator had to go like q to the fourth too, which is a very fundamental. It was one of the first kind of non-trivial and one of the few non-trivial fundamental results after Laughlin in this whole area was the GMP q to the fourth thing. But they didn't actually analyze what the q to the fourth on the top line of their expression was. They just noted it went like q. If you actually look at it, what it is if you take the true ground state and you do an area preserving linear deformation, which basically stretches it in one direction and squeezes it in the other direction, the whole ground state, right? And you calculate the expectation value of the Hamiltonian. Obviously, it's no longer the ground state, so the energy goes up quadratically, right? It actually goes up. It's regulated by a fourth order tensor, and that's precisely the one we see here. The long wavelength one is actually precisely this fourth order tensor that was somehow that one. Okay. So that tensor you can actually, for long wavelength things, is actually precisely the content of the top line of the expression that the wavelength goes to momentum goes to zero limit, q tends to zero limit of GMP. That's the controlling thing, and it's basically you use the true ground state of the Hamiltonian, you squeeze it with a unitary the unitary generator of squeezings, and you evaluate that as a function of the squeezing. The squeezing is a quadratic parameterized by a quadratic symmetric tensor, and so you got a thing with two indices, four indices. It's really two indices because the first AB is a set of three possible symmetric combinations, XX, YY, and XY, and the other one is that. So, yeah.
But you need a Hamiltonian to evaluate.
Yeah, the energy cost is the stress energy. I mean, you need that once you've got you're doing a strain on it, right? To know what the stress is, you need the Hamiltonian, right? You have to find what energy cost the strain does for you to find out what the stress is. Okay, well, what actually happens if you look at these things, it has the effect of if you model the bare thing by a little hole, right? You cut out a little cylinder of the charge density in the Chern-Simons thing. Just say that the missing charge is the original density of the fluid with some fraction of the composite boson thing. You actually find that this thing, well, it actually can allow the hole to fill in, right? Because it pushes. It doesn't change the charge, but it pushes it out and does something like that to the thing. Okay, so what else do we know from this? Well, just as a discontinuity of the polarization in a paraelectric material, or rather a polarized material, a ferroelectric material. If there's a discontinuity of the polarization at the boundary, then there's a surface charge which is equal to the normal component of the polarization at the boundary. Right? Well, the same principle applies to the quadrupole. If there's a discontinuity of the quadrupole density at the boundary, you get a surface polarization on the boundary. So in particular, we see that if we know Q at that point on the boundary, in this little element of the boundary dx of the boundary curve, that tells us what the dipole moments of the little boundary thing is. Right? Another interesting formula is the whole viscosity, which has dimensions of Planck's constant per unit area, has a very simple looking expression in terms of the things. It's just given by, it's got two basic ingredients, the Faraday tensor and the quadrupole tensor, right? Since the Faraday tensor is like B and the quadrupole tensor is an energy, EB is h bar over a length squared. So we see that the viscosity, of course, has the correct dimensions of Planck's constant per unit area, action per unit area. And voila, so that's actually And of course, it's got the two ingredients. It's odd under time reversal because of the Faraday tensor, et cetera, et cetera. So it's actually a very clean expression for the fundamental expression for the whole viscosity. The previous expressions were all based on stuff to do with rotational invariance and use concepts like the orbital spin per electron and stuff like that, right? Here it's the quadrupole density, which actually doesn't, which is a non-microscopic property. It doesn't tell you what the quadrupole moment of the composite boson is, because this formula doesn't actually tell you what the composite boson. This is a non-microscopic thing. You just know you've got some quadrupole density and you've got some Faraday tensor, and that's the local. They have local values, and that's the local value of the whole viscosity. Okay, so what should we say? The quadrupole density is actually analogous to the spin density of an easy axis ferromagnet. Okay, so if you want to write down an action for a ferromagnet, you of course have to write two parts. There's a Hamiltonian part, but since you don't actually have kinetic energy in magnets, you instead have a Berry curvature term, in fact, right? And so, of course, the part which is proportional to the time derivative of the order parameter field is linear in time derivative. And of course, it has something like this was a kind of paradox for a long time, way back in the 70s and 80s. I wrote an early paper on this stuff because people were actually writing papers discussing, they were basically discussing without knowing they were discussing it, which was the correct form of the Dirac potential, vector potential. Do you put the whole singularity at the South Pole, or do you share it between the South Pole and the North Pole? There were papers written in the magnetism literature which were basically debating that question, which was the right one. Of course, you realize it's the correct form, which is it's a Dirac potential. So the only thing is that it basically corresponds to a uniform magnetic flux leading an abstract sphere, which is now the group space of SO3, which is the space of the ferromagnet. And so if I actually look at the Dirac potential written for the ferromagnet, let's see if I can go back to it. Of course, you have to choose some arbitrary direction, which of course is the Dirac singularity. Take the cross product of the two unit vectors. That vanishes at that point, but you divide it by 1 minus a dot product, which goes to 0 at that point too. So you got a nice singularity at that point. But when I take the curl of this thing, of course, I just get the relations of the Lie group, right? The SO3 Lie group in this situation here, right? Well, the quadrupole algebra actually derives. I think I skipped that. Let's get back. Went past that. Oh, okay. But where does the quadrupole algebra come from? It actually derives from the splitting of the electron coordinate in the Landau level into two parts: a guiding center and a Landau orbit radius vector. Right? So if you've got Landau quantization, it means that all the orbits in the Brillouin zone on the Fermi surface, they're closed. If you have open orbits, you get back to where you started from after a certain time, but you're shifted by a reciprocal vector, right? You don't get Landau quantization, but you get Landau quantization only if the orbit is closed and comes back to where it started from. And once you've gone around the orbit once, you didn't advance by a reciprocal vector like you do on an open orbit. And once the orbit is going around in a circle, it's got an average position, right? So they don't have to be at the origin in K-space. I mean, in the Dirac model, they're sitting at the Dirac points, that they surround the Dirac points, whatever. And if you break the hexagonal symmetry of the graphene sheet, then they move around to arbitrary points in the unit cell. So you've got these closed curves, and the Dirac orbit the momentum has a mean value, and basically, of course, the nice thing in Landau orbits is that the shape of the orbit in real space is basically the same shape as the orbit in momentum space, but rotated 90 degrees by the Faraday tensor and rescaled, right? So the we can define the lambda radius vector. Whoops, is I call it R tilde, is related to the momentum of the lambda orbit. And the key thing is that the electron coordinate is split up into two parts. The guiding center, which is the mean position of the particle averaged over its orbit. If it's not a round orbit, it may be going slower on one part of the orbit and faster on the other part of the orbit. So it's whatever the mean position is. And defining it that way, that the expectation value averaged over the whole orbit of the lambda orbit radius vector vanishes, is actually telling you that there is no dipole moment. The lambda orbit has zero dipole moment relative to the center, the guiding center. Okay, it does have a quadrupole moment. Okay, it's not a flexible quadrupole moment, but there is a quadrupole. So the lambda orbit also has a quadrupole moment. It's part of which is part of the viscosity. Okay, and so this decomposition of the coordinates which commute into the two parts which don't commute have equal and opposite chiral commutation relations or quantum geometry is completely fixed by the condition that the lambda orbit has no dipole moment relative to its guiding center. Okay, so again, a static, if it's just sitting there, as in the integer Hall effect or whatever, it's kind of got, is again satisfying this condition that the ground state has inversion symmetry. Okay, so then if I look at the algebra of these things, right? So the R commuting with R is X commuting with Y is L squared for the guiding centers, and X commuting with Y is L squared, the magnetic length squared for the lambda orbit, and it's equal to minus the magnetic length squared for the other ones. So when they add up, they commute. So the generators of error-preserving deformations are actually, of course, the quadratic things, the symmetrized tensor RA/RB, the anti-commutator, and these.
R is the guiding center.
R is the guiding center. The lambda orbit part obeys the same algebra with a minus sign I've actually left out a minus sign I see in that commutator. Obviously, the commutator has to have an I in it, not a minus sign. It should be I. There's a misprint. Okay.
But the point is that the quadrupole moment is defined in terms of the guiding center radii, not the lambda.
There's also a quadrupole moment for the lambda orbit, which is defined similarly, but actually got a minus sign in the definition. Okay. So the commutation relations are this. They're actually a presentation of various algebras, SL2R or SO21, U11, etc. It's the non-compact version of SO3, right? Where you go to the hyperbolic plane rather than with constant curvature, rather than the sphere with constant curvature, constant negative curvature. And okay, so in fact, if I want to write down the action this way, it's of course, because it's basically a slight variation on the ferromagnet. It looks very similar. It's got a, if I use this G, if I use the kind of map it to something like a metric, except the metric will not be insisted to be positive definite. It could be negative, right? Actually, it can be indefinite too, for that matter, in this algebra. It just depends on the values of various things. The Dirac potential is very similar. I have to choose some arbitrary metric, call it G0, where the singularity is going to be the metric is just a way of a coordinate on the hyperbolic plane, right? And actually, depending on the sign of the trace, it's either the upper one or the lower one of the two. And so again, it looks like a Dirac potential. It's singular when the metric is equal to G0. The top line vanishes, but then the bottom line diverges. But when I take something like its curl, I pick up the commutation relations of the group, which is all that matters, right? Okay, so how much time do I have? So okay, The remaining issue, which I'll discuss next time, is what role, a very interesting issue is what role, if any, the Virasoro algebra of, so there are two anomalies in quantum Hall systems. There's the U1 anomaly, which is the quantum Hall effect itself, which says that the commutation relations of the edge charge densities are basically the whole conductance times h bar times the derivative of a delta function along the edge, and the other one is the Virasoro anomaly. So actually, I will make the point that the general belief is, the understanding now is that the edge states of quantum Hall systems, well, they're not conformally invariant, okay, but they do have a Virasoro algebra. So actually, this quantum Hall systems are a completely independent physical occurrence of the Virasoro algebra, which is actually why stuff from conformal field theory has resonated with, because the conformal field theory stuff has a lot of the right ingredients. It's got a Virasoro algebras. It's actually got the right kind of braiding relations between the topological defects. It's also got conformal invariance, which is connected with rotational symmetry, which is not part of it. But the part of the conformal stuff, which is to do with the topology of the excitations and the Virasoro algebra, is correct, is good, and the other stuff isn't good. And you actually find that, you know, some of the results you obtain are kind of misleading from because they're non-generic, but some of the results are good. So the Virasoro algebra, one doesn't need to worry about this kind of discrete quantization in units of integers around the thing. We don't need to have m squared, m cubed minus m. It's just a third derivative of the delta function, because this is dimension h action over length squared. So the anomaly is action squared over length to the fourth, which is why you need a triple derivative. And if you have a spatially varying velocity going as you move around the edge, the velocity is changing its position on the edge, then you find you get a slight, just like I think there's a thing where you get, if you put things on a curved space-time, there's some little anomaly in the stress energy tensor. Here, the stress tensor along the edge, which is just the pressure. The pressure is actually higher when the velocity is kind of going through a dip, and there's something like a h bar squared correction to the pressure in the other direction when you go over when you reach a maximum velocity and you come down again. But that doesn't seem to be very significant, right? The interesting thing, of course, is that the Virasoro algebra is kind of measuring somehow then the difference between the number of right moving degrees of freedom per unit length and left. But that's a very interesting question: to what extent the Virasoro algebra is of the edge is present in the bulk, because current theory says that the bulk is described by topological quantum field theory, and certainly in the kind of triangle relations or whatever, the pentagon relations or whatever they are of the topological quantum field theory, you do have C entering, but you only entered an exponential form. It's only things like e to the I times 2 pi c over 24 or 8 enters. So it's not, the topological quantum field theory doesn't apparently have a role for c as a number, only as an exponent, only as it's kind of modulo something, right? And the question then is to what extent it's a bulk property. Okay, let me quickly, so that actually is some taken from an earlier version of this talk, so I just wanted to say a few things. That's repeating. Okay, one thing, one point I made, actually, a surprising point, that you learn from the inversion symmetry that the common divisor of P and Q cannot be greater than 2. Okay, where does that come from? It actually says if you look at put things on the torus, right, and you come up with what the correct many-body translation operators are. The torus is interesting because you have an irreducible kind of periodic fluctuation on the torus. There's a minimum translation distance which is compatible with the boundary conditions. So if the length of the boundary if the area, if you've got a primitive repeat distance of L in this direction, the smallest translation you can make in that thing is L divided by n phi, the number of fluxes through the torus, which has to be anyway. When you do the many-body thing, you end up with a scheme of quantum numbers, and inversion symmetric states can only occur. You've got a kind of boson zone which emerges from this irreducible little very tiny periodicity on the torus. So there are only 4 possible inversion symmetric values of this many-body quantum number. So an inversion symmetric state has to lie at one of those 4 values. And one of them is a standard one, 0. But there are also these other ones, pi, 0, and pi 0. And the more Reed state, which initially people would have said was 1/2 filling, is actually 2/4 filling, right? And in fact, we know that now because we know the elementary charge on the excitation is 1/4 of an electron charge. But it's actually telling you that if I take the maximum group of characterization of this quantum number, I will actually split my topological multiplet up into, in the more Reed case, it only exists on the 3 outer ones. But another fundamental principle tells you that there should be no difference between any linear combination of states in the topological multiplet because they don't connect to each other, right, properly. So I can't use a scheme to characterize it which distinguishes members of the topologically generate multiplet. So what it actually means that the smaller, instead of classifying things by the smallest commuting set of translations, you have to classify them by double that. If you double the translation in real space, you shrink the boson zone by a factor of 4. So you actually map this largest possible boson zone into a quarter zone where all those states are at the proper momentum inversions, only inversion symmetric value k equals 0. So actually telling you that since Q enters into that, you should be using the real Q, not the kind of most primitive version, and that's actually, but there's no other possibility, so you can't have any, because you've only got those 4 points which are inversion symmetric. So inversion symmetry forces you to, so what used to be called what have been called the even denominator net states, the things that everyone used to think that P and Q were relative primes automatically, right? And so it was like a shock to find something at 1/2, which is really 2/4. But the basic issue is what the value of P times Q is, right? P times Q is 8 for that. So the more Reed state is a U1 level 8. And -1 to the 8 has to be equal to -1 to the 2 for bosonic things, because you've got 2 particles in it. 2 fermions, and -1 to the 8 is equal to -1 to the 2, while -1 to the 4 is not equal to -1 to the 1, which is a violation of the odd denominator rule, right? Yeah.
You said that more Reed is U1 to the 8, but isn't it the non-abelian?
U1 to the 8.
That's an abelian.
Yeah, it's U1 to the 8 times Z2. U1 level 8. So the non-abelian ones, the topological field theory has got can be viewed, I think, as I'm not sure if there's some co-setting involved, but it's the U1 part is U1 level 8, and then it's multiplied by the Z2 case, right? And for the Reed with I type thing, there's a Reed with I at 3/5, and I forget what it is. Yeah, but basically you can work out what the correct classification is, right? So the other thing on that is, okay, I wanted to just show some pictures. So yeah, these bubbles that get occupied, because the bubble is an empty region, a hole in the background, and the particles basically repel each other. You get the quantum Hall effect from this repulsive effect. Then there's a kind of potential which is minimized at the center of the center of the bubble is a place which is like furthest away from the other particles, right? So the bubble should adopt its shape approximately to according to what the dielectric tensor is saying, except there's also effects of the projection into the lambda level. Okay, we'll come to that. But basically, we have a little. So we can think of the Laughlin quasi-particle, or Laughlin composite boson as these 3 units, 3 empty orbitals, and you fill the lowest one with 1 electron. And the 2/5 state is something similar, where I have 5 orbitals, and I fill the lowest 2 according to the Pauli principle. Okay. So actually, let's think about what. First of all, in composite fermion picture, let's see, did I actually put it in here? Okay, let's add some charge to the 1/3 state. Okay, so one issue has been that there's a big lack of symmetry between the quasi-particle and the quasi-hole in the Laughlin state, right? The quasi-hole is just it's just out of flux, right? So it just makes a little empty hole. It's actually a little bubble which contains nothing. It's a bubble of 1 flux quantum with no particles inside it. Right? Well, if I want to add an electron to dope the Laughlin state, like doping a semiconductor, right? Well, let's stick an electron in. It's going to, well, the first place it's going to go in, it's going to go into one of these composite bosons and jack it up from being 1 particle in 3 orbitals to 2 particles in 3 orbitals and convert it to being a fermion too, I guess. But that's an unstable thing. And what actually happens is I can then let this object recombine with 4 neutral 1/3 droplets. And that's a total of 6 orbitals, 6 electrons in 15 orbitals. And that's actually going to split up into 3 2/5 droplets. So the 2/5 droplet, the droplet of the next state up in the hierarchy scheme, as I start to add electrons to the Laughlin state, I start to produce, every electron produces 3 droplets of 2/5 state, and of course shrinks the number of the 1/3 droplets. Eventually, as I fill the thing up, the 2/5 droplets will coalesce, and I'll have a 2/5 state with a few 1/3 holes left, droplets on. And of course, you can start the other way around. If you remove a particle from the 2/5 state, so you take out 1 particle and leave it in the 1/5 charge state, then it can combine with stuff, and you'll create five quasi-particles with charge minus 1/5 relative to the background, and those are actually droplets of the 1/3 state, which carry a relative charge of minus 1/5 when they're swimming in the background of 2/5. So you have a kind of symmetric pattern like that, and the final thing in that is that if you, in a crystal, I'll stop here, the unit cell doesn't move around. I dope my unit cell. The charge transport is not, well, unit cells, of course, are locked together in a crystal, right? But of course, what's moving is the extra electron that I shoved into the unit cell will kind of hop from the filled one to the neighboring empty one and can hop around. Here, what happens if I actually if I've actually created a local quasi-particle, which is a droplet of 2/5, it's not the droplet that moves. They're all kind of packed together in this kind of quantum incompressible blob. But what will move is an electron can hop from this one to the next one, and it takes with it two flux quanta. That's precisely the composite fermion. So the composite fermion can be viewed as the object that moves hopping between the unit cells, which are the composite bosons. And so they're very useful for discussing charge transport in a dope thing. And I guess we've run out of time. So I guess I'll get back to some stuff next time.
Regarding the quadrupole density, so the tensor, stability tensor chi ABCD, you get it from the static structure factor terms that are ordered to the 4.
Yeah, you can at least evaluate. I mean, it's going to depend on Q, right? So there's going to be some non-locality in the thing, which will give you some dispersion relation to the. But if you just take that, you actually reproduce the long wavelength limit of the GMP, because if you look at the formula for GMP, it's actually precisely the result of acting with the generator of strain. You act on the true ground state with that. You can make a deformed ground state, and then you take the expectation value of the Hamiltonian in a deformed ground state, and that clearly has to be higher than the original one, which was a true ground state energy, right? And so it goes up whether you squeeze it inwards or outwards, right? And that provides that the tensor, at least the long wavelength limit of that tensor.
With the sort of big goal of studying the quadrupole, there are higher.
Yeah, it's what we were calling the graviton until recently, and so it actually turned out that the excitations they're not chiral topological excitations that only go one way around, but they do have a chirality. So if I have a ferromagnet the analog of a ferromagnet, the actual the topological part of the action, which is the part linear in time derivatives, that's completely isotropic, right? It doesn't matter what direction you're pointing in. It's the Hamiltonian that determines what the preferred direction of the. So the analog should be with a easy axis ferromagnet, right? Or something with a Zeeman term, probably, right? So the actual ferromagnet will want to point in the direction of the Zeeman term, and it will kind of. Then you do then if you want to look at the collective excitations of that thing, you'll have small harmonic kind of fluctuations around the, basically you've got Sx commuting with Sy is the expectation value of Sz plus delta Sz, right? And you forget about the delta Sz part, and just so X commuting with Y is a C number, the expectation value of Z, and that gives you the Zeeman precession, right? Now, again, in the ferromagnet, if it's maximally pointing up, you lower the angular momentum by going down, so these things carry an angular momentum. There's a precession direction, right? Well, in the on the hyperbolic surface, there are actually there are these two separate hyperbolic cones, one pointing up and one pointing down. And they're associated with whether the trace of the thing is positive or negative. Since I'm really going to think about the kind of large spin limit where we're talking about positive definite or negative definite, then the positive definite quadrupole things that you excite upwards with the one-handedness, and the other ones you excite down. So the issue has been, so it seems to be that in a more complicated system, like a 2/5 state, right, where you have a K matrix, or even anything with more than one component in it, you actually seem to have a separate Virasoro algebra for each independent component, and a separate and going with that is a separate quadrupole moment. So, for example, if I take the 2/7 state, the 2/5 state, both quadrupole moments associated. The way I formulated, you've got the 1/3 on top of it. You have a condensate around the 1/3, which is the daughter state, but you can do it various ways. But both of those have the same sign of the quadrupole moments are both positive definite. But in the 2/7 state, one is positive definite and one is negative definite. So one we associated with the analog of Zeeman precession that way, and the other way. And in fact, that's what one sees, that you can actually see that the collective mode at long wavelengths is chiral. I mean, in a sense, it's angular. If you make it rotation invariant for convenience, right, you find then one has angular momentum pointing one way, the other way. And indeed for 2/7, it looks like you've actually got two independent. So actually, you need to write a more general Hamiltonian way. There's actually one quadrupole mode for each independent fluid in this multi-hierarchy scheme, and then they will all have their, and they individually will either be positive or negative definite, which will give them a chirality, and then there'll be some kind of more complicated kind of spectrum of. It's a bit like if I have a unit cell in a crystal with more than one atom in it, right? I start to get so in a crystal, the geometrical modes are the acoustic phonons, which are really changes the fluctuations of the shape of the unit cell. But then there's the optical phonons, which are the kind of relative fluctuations of the stuff inside the unit cell. And basically, I've got one set of optical modes for each atom in the cell. It seems like in these more complicated hierarchical kind of quantum Hall states, the ones at least the K matrices give you and things, you're going to get one of these, you're going to get independent, if you can organize it hierarchically, then each of the, there's a separate kind of quadrupole associated with each fluid component. So you get some complicated structure like you do in crystals with more than one atom in the unit cell.
So they're both right. Connected field theory that includes the gauge field we wrote in the beginning, and then to add a metric that fluctuates.
That's really, yeah, the quadrupole, now replace the metric with a quadrupole moment, and actually it's got this feature that it can either, yeah, it's actually a signed quantity, right? So it's actually sometimes positive, some of them are positive and some of them are negative definite. And in fact, the whole viscosity, if you do an entanglement spectrum by cut on a cylinder, if you do the von Neumann entropy, you find it's proportional to the length of the length of the circumference, but it's non-universal apparently, right? And then you pick up a topological term of order L to the 0, which tells you about the quantum dimension of the topological quantum field theory. And if you do the momentum polarization, because you're actually looking at P times L, there's a momentum per unit length, but actually you're multiplying it. You actually, the Virasoro index is the momentum times the length. It's PL over H bar, not just P. So momentum is, there's a momentum or dipole moment per unit length. And now, anyway, you've got another L floating out. So the leading term goes like L squared, and it's precisely the length of the circumference measured using the quadrupole moment like a tensor, except it could be signed, it could be plus or minus, because it's not a positive or negative. It's a tensor. It seems to be generically a sum of definite tensors, but neither, some positive and some negative. So it's a signed version of a metric. And then the next order down, I'll come to that, has some interesting, tells you about C in a very interesting way, which I'll discuss next time.